Hi, my name is Shariq Haseen, and I'm a chemistry graduate student working with Dr. Peter Kroll. The topic of my poster is about the structure search of silicon nitride. So if we take a look at the introduction, silicon nitride is a ceramic with high thermal stability and enhanced mechanical properties at elevated temperatures. It exists in different crystalline forms like alpha and beta silicon nitride. In 1999, gamma silicon nitride, a high pressure form, was synthesized. And this high pressure form differed from alpha and beta silicon nitride in that it had much higher density, along with higher hardness and elastic property values. So considering that, along with our recent observation of a hypothetical Pa3 bar silicon nitride, we decided to do a full structure search of silicon nitride. And we were looking for structures with promising properties that could potentially be synthesized. So our method is straightforward. We rapidly generate thousands of silicon nitride structures using molecular dynamics simulations. All of these structures are optimized with quantum chemical calculations with density functional theory. So quantum chemical calculations are more rigorous than molecular dynamics simulations, but at the same time are far more computationally expensive. Anyway, the advantage of using these molecular dynamics simulations is that they produce structures that are already very close to how they'll look like in density functional theory. The only issue is that the energy distribution of these molecular dynamics structures are quite narrow, or is quite narrow, and we do DFT calculations to remedy this. So the structure search produces many thousands of structures, and a lot of these structures have low to no symmetry. Here you can see some structures that have high symmetry and that are only just above the energy of alpha and beta silicon nitride. And we find these structures by looking in these dark regions or the low energy regions of these energy contour plots. The choice of the starting density does determine the kind of structures we get out. So using low densities like 2.8 will result in finding low density structures. Using high densities like 3.4 and 3.9 will also result in finding low density structures, but we'll also find some higher density structures along the way. And so since the question is, we're looking for whether any of these hypothetical structures could potentially be synthesized. And we can answer that in part by looking at the thermodynamics. So the lowest energy structure at any given pressure is the most thermodynamically favorable structure. And you can see that alpha silicon nitride and gamma silicon nitride dominate for most of the investigated pressure range. But at these so-called negative pressures, we find the PBAM silicon nitride to be the most thermodynamically favorable form. Anyways, we're also interested in the mechanical properties of these structures. So we calculate the bulk modulus, which is the resistance to compression. And you can see that these structures with similar density to alpha silicon nitride have much lower bulk modulus values, and this is quite interesting. Anyways, we can briefly talk about the insertion of titanium into silicon titanium nitride. And a mixed spinel silicon titanium nitride was synthesized only last year. We did a combinatorial search looking over many thousands of structures to determine the energetics of the formation of this ternary material. What we found, though, was that the formation of silicon titanium nitride was always going to be unfavorable thermodynamically, or as we calculated anyways. So we proposed that the synthesis was observed experimentally, likely due to slow kinetics. So in summary, we generated thousands of structures of silicon nitride. None of the hypothetical structures we found, though, were thermodynamically favorable for any of the positive pressures we investigated. And at these negative pressures, the PBAM silicon nitride emerged. And it's possible that this could be synthesized using tensile stresses. The next step is analysis of ring statistics, potentially looking at different starting densities along with maybe differently sized models. And in a final note, the experimental synthesis of this mixed spinel silicon titanium nitride was probably not due to thermodynamics in terms of the formation, but probably due to kinetics. So that's it. Thank you very much for listening. This project was funded by the NSF PIRE project, and supercomputing resources were provided by Texas Advanced Computing Center. Thank you very much.